Okay, so we left off on section 7.2 last time. 7.3 we are not including in this week. So I'm going to pick up with 7.4 where we solve inequalities. We will use what's called set notation to express answers when we solve inequalities. So we need to talk a little bit about that. A set is a collection of objects, and a union between two sets, as noted there, A union B is how we read that, contains elements that belong to either of the two sets, either A or B. So it can be in either one. And then the intersection, A intersect B, as you see there in the symbol, contains elements common to both of them. So they have to both include that element if it's going to be in its intersection. They can also be expressed in various ways. Set builder notation, like you see here, is read X such that is what that vertical part is. X is less than 3. So that set builder notation example is read X such that X is less than 3. So the set would include numbers like 2, 1, 0, -1, things coming down from 3. Another way of expressing that same set is in interval notation, and that is the same set expressed in interval notation. Um, the right-hand bound is the uppermost number, and with a parenthesis, that means it's not equal to that number. So notice how on the right-hand side of that interval, there's a 3 with parentheses. That means it needs to be less than 3, not including 3, but not equal. And then the left bound tells you how low the set goes, and we have negative infinity there since it's less than 3, it's not really bounded, or it doesn't have a lowest number, so we would express that with negative infinity. So that's just one example. We'll see some others as we work through the examples you see. To solve an inequality, we use the same sort of strategies that we talked about for solving an equation, except if you multiply or divide both sides by a negative number, you have to reverse or turn around or rotate, switch around the inequality symbol. And we'll see some examples of that. Let's first just sort of talk through the example where we're to solve 3 halves x minus 2 greater than or equal to 4, writing the solution in interval notation. So like that. First off, we're just going to sort of write this down in our similar to equation form and then use the same sorts of strategies we would for solving an equation. So we've got a variable term minus a number greater than or equal to a number. So we need to move that number 2 to the other side to join that 4, just like we would when solving an equation. So then we have 3 halves x is greater than or equal to 4 plus 2 for 6. And now we're at the multiplication and division stage. Now that exception that we talked about, notice there's no negative with the variable x. So we're not going to flip around the inequality sign since we're not multiplying or dividing by negatives. We have a positive 3/4 in this example. What I suggest when you have a fraction and you're trying to undo this is start with multiplication of that thing that's in the denominator. The 2 times 2 times on both sides. And what that does is it sets you up to divide this quantity that's in the bottom of the fraction, the denominator, leaving you with only what's on the top and the variable x. So we've got 3x remaining on the left-hand side, greater than or equal to 6 times 2 for 12. Now we have 3 times x to counter with division. Divide 3 on both sides, leaving us with x is greater than or equal to 4. Okay? Now we want to express that in interval notation. So something similar to this. However, this time notice we have an equal bar. In that other example, no equal bar up under the inequality of the less than sign. This time we have greater than plus the equal bar up underneath. Now, if it's greater than 4, that includes numbers like 4, greater than or equal to 4, it includes 4, it includes 4.5, 5, 6. So going up from 4. So 4 is going to be our lower bound, the lowest number in the solution set. And so we would put it on the left side of our interval notation. I'm going to come over here to the right of our solution in inequality form and write it in interval form. That's going to have a 4 on the left bound or lower bound. Also, with the equal bar expressed, we change from parenthesis to square bracket to indicate it can be equal to 4 in this case. And think about if you're just going up from 4 with no stopping point, then the way you would express that is with positive infinity. So we do comma, and then the upper bound in this case, there's no number to stop at necessarily, so we're going to put an infinity on the right of our interval. Always, when you express infinity, if it's negative infinity on the left or positive infinity on the right, like we have here, always use paren on infinity side, regardless of what the symbol is on the number side or the bounded side. So for this particular example, we have 4 to infinity, and I'm looking for, see, that doesn't match our, oh, let's see. There's a typo here. So ignore the example right here. There's a typo. Uh, it should not flip to 2/3 when you add 2 to both sides. It should remain 3/2 like we were given in the original expression. So there's a typo there that's why it looks a little bit different and that's wrong. So follow what we did on the right-hand side there. You should end up with x is greater than or equal to 4, and that corresponds to that interval, square bracket 4, comma, infinity, paren as our final answer. Okay? So let's work through some of the practice problems for a little more clarity. And some of these first ones are just to get us used to set notation and how to identify what is included. So remember this symbol here, the U, means union. And when creating a union of two sets, we include everything that appears in either one of them. So A union B is the set with everything. So I'm going to start here and just start writing some of these numbers out. -3, -1, and 3. I'm just going to place that over here because notice in the other set we have some other numbers here that would go in between. And so we've accounted for everything in A for our union so far, and then we need to also incorporate everything from B. So that includes 0, 1, and 2. We already have 3 in there. So everything from B is accounted for now too in our union. It works a little bit differently for intersection. That upside down U symbol indicates intersection of the two sets. And so A intersect B will include only the elements that are in both of them. So as we scan across A, 1 and 2, and scan across B, 3 and 4, we notice that none of those elements or numbers match. And so when we start to express which ones match between the two sets, we come up with what's called an empty set. There's nothing that's going in there because none of those numbers match between the two sets. Now let me come back to the other example just so you can see a little bit of one where there would be something. If we come back to this first example and do A intersect, so notice how I flipped over the U, I'm writing A intersect B now. For the first example, I scan across both of them and I notice there's a 3 in both of them, positive 3. See? And so that is in their intersection for that first example. A intersect B on number 1 of that first example is 3, the set containing 3 in that case. So that's what union and intersection mean. The third example that we're looking at here says x such that x is less than or equal to -4. Convert that to interval notation. If you recall from the first example we did, when we solved the inequality, we came to something that looked like this, and then we made one last step to convert it to interval notation. That's sort of what we're doing here. The solution is considered x less than or equal to -4. And so what is that in interval notation? Things that are less than would be like -5, -6, -7, going to the left, envision that. And so -4 sits at the very rightmost or upper point of this set. So -4 is going to be on the right-hand side, comma, here. Something going to the left or the lower bound on the left of -4 in our interval. So let's come back to what boundary symbol does -4 need on it. Notice there's an equal sign in this one. So we're going to use square bracket as the boundary symbol on -4. Now, what's the lower bound of this interval? We don't have any indication that it needs to be greater than some number. So as we continue less than, less than, less than, more and more, unbounded means that we want to write that or express it as -infinity. Remember, every time we use an infinity as a bound, we're going to place a parenthesis on that side. So that's the interval notation for that example. We're going to solve the next one and then use interval notation to express our final answer. We have 5x plus 3 is greater than 2x plus 12. So notice we have variable plus number is greater than variable plus number. So what we have to do in that case is start subtracting or adding on both sides things that we can join to the other side. You get the variables on one side, numbers on the other. You can approach this in two different ways. I am just going to choose to subtract 3 on both sides to start with. You might do something else, like subtract 2x on both sides to start with, but I'm going to start with that. And I have eliminated the 3 on the left by doing that. And so I'm looking at a 5x left over. It's greater than. And then 2x, I operate on the 12 and then -3. So 12 minus 3 is 9 positive, so I write a plus 9. Then let's come over here and give ourselves some room to continue working. Notice we have variable greater than variable plus number. We need to move that variable term now. Let's subtract 2x on both sides since it's implied to be positive with no negative in front of it. We need to subtract it on both sides so that it's gone from the right, leaving us with just this 9 coming down. And 5 minus 2 gives us 3 on the x term. Now we're at that stage where we have something times the variable, 3 times x, so we need to counter that with dividing 3 on both sides. And that will eliminate the 3 times, leaving us with just x is greater than, and then 9 divided by 3 is 3. So there is our inequality notation, x greater than 3, but we need to write it in interval notation. So Let's convert greater than 3, 4, 5, 6, 7, going up and unbounded on the right, so positive infinity, we can go up to, and 3 is our lowest number. We can be strictly greater, not equal to 3, so we need to use a parenthesis in that case. Like the very first example in the description of the section at the top, where it doesn't have the equal bar up under the greater than symbol. Those are cases where you place a parenthesis on the number boundary. So just as a recap, brackets when there is an equal sign on that number boundary, paren on the number boundary when there's no equal sign, and always paren on infinity sides of your boundary. Okay? Let's take a look at this last example for section 7.4. The student test scores are 72, 77, 79, and 82. The final exam counts as two tests. What must the student earn on the final exam to have an average of at least 80%? Now, I'm not so interested that you be able to take a worded problem, convert it to inequality, and solve the inequality. I'm more interested in that last example we did, and that you're comfortable with the interval notation expression, like that we've talked about so far. It's just kind of taking it an extra step, giving you a little more depth. And so let's think of averages. 72 plus 77 plus 79 plus 82 plus two tests equivalent for the final exam, which we don't know the score, so plus 2 times that final exam score. And the idea of average, you need to divide by the number of them, right? And so we've got 1, 2, 3, 4, 5, 6 tests total. So we divide by 6 to get the average of all those scores. And then that we want at least 80%. Now think about at least. If I want my grade to be at least 80%, that means, I'm shooting for B, right? And that would be like 81, 82, so forth, 80 even, but not 79 or lower. At least 80%, we're shooting for higher than that. So this needs to be greater than or equal to 80. All right, so there's our setup. Now let's solve this. Let's create a little more room for us here. So we can solve. Okay, we've got 6 on the bottom of a fraction, and that's prohibiting us from doing operations simply anywhere in the solving process. So let's get rid of that 6 to start with, and we can do so by multiplying it on both sides. So over here, we do times 6, and then on the right-hand side, times 6 as well. That divides it evenly over here, and so we are just left with what's on the top, 72 plus 77 plus 79, 82 plus 2x. Greater than or equal to 6 times 80. Take the calculator and do that calculation for 480. Then we want to add some of these like terms that we see on the left. Notice we have a lot of number terms. This one, this one, this one, and this one. So let's add those up. 72 plus 77, 79, and 82. And just confirm that on your calculator. Let me just pull up a calculator here. If we can look along with that. If we do 72 plus 77, 79, and 82, we get 310. So those all combined for 310, we bring down the 2x greater than or equal to 480. Now notice we have number plus variable greater than or equal to number. So we need to move the number that's next to the variable term to the other side to join with that 480. The minus 310 on both sides. That's going to leave us with just 2x on the left-hand side. And just come into your calculator if needed and do that last calculation. 480 minus 310 for 170. We can leave that calculator for a moment. Come up here to continue our work. 2x greater than or equal to 170. Now we're at that stage where you have number times variable. So divide that quantity to get the variable by itself. Divide 2. That gives us x greater than or equal to, and then 170 divided by 2. Take your calculator for that if needed. Divide 2. We got 85. The x is greater than or equal to 85. That means 85 will be the lowest we want to earn. It can be equal, so we use square bracket on that number bound. And then we can go up to, well, we know that, in the context of test scores, our upper bound would be 100. Right? So we could express the upper bound to be 100, and that would be inclusive or could be equal to 100. And we'd be perfectly fine to have at least an 80 in the class. So we can use square bracket on that side as well. That particular example required a little bit of context thinking, which is not always involved when we're just solving those that are just a point blank math example, like the last one up here. So some interesting food for thought and depth, like I said, in understanding how inequalities might be used. I'm most interested that you're comfortable solving the inequality and converting from what you get to the interval notation. So not so much the setup from a word problem do I want you to worry about. It's more the process of solving the inequality and then that final conversion from what you get to the interval notation. I'm going to go ahead and pause this or stop this here and pick up with another video on 7.5.